Alrighty, guys. So we can take some time to go over some of the questions that you really want me to go over. I know there's one question that everybody has been like emailing that, and that's definitely number three. So I'll be going over that. So this is a classic kind of question he definitely would ask about like oxidation states, right? And they're just asking about the oxidation state on the silicon atom in this case, right? So there's a couple of things we know. We know for a fact that fluorine is always -1. That's because it's the most electronegative, and that's one of the rules we need to know. So because of that, we know that fluorine has to have a -1 charge, and since there's six fluorines, that must mean it's -6. I forgot to also mention that compounds, unless otherwise like stated, like polyatomic ions or whatever, right? They're always chemically neutral, meaning that this overall charge is zero, right? So this is -6 there. All right. Hope that makes sense. And then likewise, there's a couple ways you can go about this, right? One is you can just try to figure out the oxidation states of nitrogen and hydrogen. So like that would be hydrogen is always +1 like that. Um, and then because it's +1, the overall charge here would be +4, and then nitrogen would be -3. All right. And the reason why that would be, is, well, yeah, like with nitrogen, it's typically is -3. Um, the reason why, though, we will know this for sure is that ammonium is a polyatomic ion, right? So this charge has to equal +1, right? So it's gonna be +4 and then -3. Yeah, you could like identify it like this, right? And I think many of you guys do that. Um, And then, yeah, as a result, this whole thing should be +1. However, because there's a subscript of 2, this overall charge is going to be +2. All right. And so now we have +2 plus silicon, which is X, right? Plus -6, right? Equals 0. So what value here in X what value should that be in order for everything to equal 0? Has to be +4. Okay. So that's why the answer choice is D. Does anyone have any questions about that? Comments, concerns, thought processes you want to run by me? Okay. Is there any other specific question you guys want me to go over with this page? Feel free to, this is your time, like if there's anything you want me to do, even if it's just like, how would I go about approaching a question?
Hey, Luke, can you go over number two?
Sure. Yeah. Sounds good.
Thank you.
So yeah, number two deals with, I believe it's module two. This is percent abundance. And so what they're asking is what is the average atomic mass of this, right? So the way average atomic mass, if you look at your periodic table in general, right, all those numbers, like for instance, like hydrogen has like an atomic mass of 0.08. All of those numbers are from like percent abundances in here, right? But that's just me yapping. So I'm gonna also pull up the calculator. This is a good app. It's called Calculate 84. It basically works as a graphing calculator. And it's good because I can show you guys how I would go about these questions. So what I see here is there's three isotopes, right? And we don't know the percentage of this one, and we're asked to find the atomic mass. So automatically, what I would do is I would say, hey, because there's 90.92 and an 8.82, I should probably subtract both of those things by 100, right? So 100 minus 90.92 minus 8.82. And the reason being is that percent abundance is out of 100. So if we know the percent abundance is of two of these guys, we can figure out this one, right? So that's what we'll do. Let me erase that. Okay. So I'm gonna put in my calculator 100 minus 90.92 minus 8.82, and you get around 0.26%. All right, that's what you get. And so now what we can do is we can take all of these, and all you have to do is simply add everything up by multiplying it accordingly. So 199.99 times, instead of it being the percentage, you do the decimal version of that percentage. So it'd be 0.9092 plus 201.99 times 0.0882. And then for the last one, this one might be a little tricky, but um, yeah, this is why it's important to know how to do the decimals, right? This is 200.99 times 0.0026. Okay. So the reason why is that it's already pretty much a decimal is the percentage. So you add two zeros, right? Okay. So now what I'm going to do is I'm going to take this expression and put it into my calculator. So let's do that. So 199.99 times 0.9092. Okay. Plus 201.99 times 0.0882 plus 200.99 times 0.0026. And I get this answer, 269 AMU. And that's choice C. All right, sound good? Okay, any other questions? Anything you want me to go over? It could be as silly as it needs to be. This is your time. Please let me know. Okie dokie. All right, then I guess we can move on from these questions. If you guys have no questions about it, please feel free to email me if you guys have questions about this first page at least. Okay, like you got today and tomorrow. I have a final tomorrow, but yeah, like abuse me, like take advantage of me. Okay. Oh, this thing is being recorded. Oh, I should not have said that. Oh no, I'm gonna get fired. I'm joking. That's a joke. Okay. Let's go over to the second page. I'll give you guys another 15 minutes to kind of go over it. And then if you guys have any specific questions you want me to go over or anything, please let me know. Okay. Yeah. Again, I added my phone to the Zoom as a co-host. And so if you guys have specific questions you want me to ask, like ask through that guy. I'm screen sharing, so I don't want I don't want everyone to see your individual message to me. But yeah, okay. I'll let you guys get started, and then yeah, feel free to shout out any questions you got. We will come back at 1:45. Okie dokie, guys. Yeah. Is there any questions that you guys want me to go over? I know I got one for number 19. Um, yeah, I guess I'll get started with 19 and ask you guys. So in this question, number 19, it's talking about this guy over here, this whole compound, but specifically it's talking about carbon A. And so they're asking what type of bond exists between the carbon and the oxygen atoms attached to it. And I really am annoyed that he used this kind of symbol because I feel as though um what's the word? The like he doesn't really explain what the symbol is, and it's kind of annoying that he didn't explain this as symbol, so I'm gonna explain it. Basically, when we're talking about any like um molecule or bond, right? There is like a way to express the direction of like where electrons are gonna flow, right? And so basically, as we know, oxygen is gonna be a lot more electronegative than carbon. And so the electrons are gonna flow in this direction. Okay. And so what that represents, right, is that all the electrons are going to be kind of not all the electrons, but a lot of the electrons are going to be around oxygen and not as many around carbon. And so another way to look at this is because there's so many electrons around oxygen, it's not going to have a typically neutral like state, right? It's actually going to be slightly negative because of all the electrons around it. And so this symbol here, I don't really know how to draw it well. I always draw it like this, but basically the symbol here represents a partial negative charge, while this symbol over here represents a partial positive charge. And so in polar bonds, I kind of spoiled the answer, but in polar bonds, right, we have an uneven distribution of electrons. The reason being is that electronegative atoms like oxygen are pulling electrons more in favor than carbon. And so for this question, I had a typo in I think I revised it, but basically for this question, number D, sorry, D would be the right answer because oxygen would have that partial negative charge. All right. Any questions or anything you want me to go over specifically about this?
Hey Luke, can we do
Mhm.
question 16?
16?
Yeah.
Sounds good. Yeah. So for question 16, we see here that we have magnesium chloride and oxygen dichloride. And so this is taking naming nomenclature. You need to know how to write these out. And so magnesium chloride would be something like this, and oxygen dichloride would be something like this. Okay? So then what we're asked is to figure out the true statements, right? And so yeah, number one, right? A 1 mole of magnesium chloride contains less chlorine than 1 mole of oxygen dichloride. This is false. This is because both of these compounds on its own have two chlorines. So 1 mole would not have any more than another mole. So that's why A is wrong. Number two, the boiling point of the magnesium chloride is lowest than it should be lower than the boiling point of oxygen dichloride. That's also false, right? We know that salts will have a higher boiling point than covalent molecules. Okay. And then C, both magnesium chloride and oxygen chloride are covalent compounds. That's also false. So the correct answer would be E. Everything is false. Okay. Sounds good.
Thank you.
Yeah, no problem. Okay. Any other questions about this page?
Did you go over 15?
Yeah, sounds good. So this question gives you not a lot of information, but STP is a really important thing. So they give you mass and they give you volume and they give you STP and they ask you to find the molar mass. And so we obviously know PV equals nRT. However, right, we can manipulate this formula. In order to find moles of anything, you have to have mass of a compound over its molar mass. And that's something that we've already talked about a bit, right? Like just if you think about how you convert mass to molar mass, or sorry, mass to moles, you have to take some mass and divide it by its molar mass to get to moles, right? That's the dimensional analysis. So like something like 1 gram of hydrogen, right? To convert that 1 mole is over 1.008 grams, right? And then that converts it to moles, right? It's the same thing with this. And so what we can do is we can plug in M over big M into the equation, and then we could solve for big M, right? So we can do MRT over PV equals big M. All right. Does anyone have any questions about that? This formula, how I got that? Because that's like the most important thing. Okay. So from there, right, what we can do is we can kind of plug in, right? We know SCP happens at 1 ATM and also happens at 273.15 Kelvin, right? So we can plug those values in. So we have 22.1 grams, and then we have 0.08206 ATM liter over mole Kelvin, right? That's the gas constant. And then temperature is 273.15 K, right? And then divided by 1 ATM times 15 liters. Okay. And then with my trusty graphing calculator, where's my graph? There it is. We can solve this. So what I would do is I'll put in the numerator, 22.1 times 0.08206 times 273.15 and divide it by just 15 because that's what it would be. And I get 33, around 33, which is the answer. So the choice would be E. Okay. Does that make sense?
Yeah, thank you.
No problem. All right. Any other questions about this page?
Can you do number 14?
14, where is that? Oh, yep, sure. Sounds good. All right. So I'm going to explain it using a reaction. Basically, right, this is a neutralization reaction. That's why it says neutralize. And we have to, it's acid base, right? So let's write out HBr plus calcium hydroxide. And I always told this in the SI sessions, but when you have an acid base reacting with each other, what you're going to produce is you're going to produce um, a salt and water, right? So the salt being is calcium bromide, and then the water is just water. And then we have to balance it. So this is going to be there. And I believe yeah, this has to be there. Okay, so balancing is really important. Then after that, what we can do is we can use the reaction stoichiometry to figure out the volume, right? So how can we do that? First, we can figure out moles. So I like to do dimension analysis as like one whole step, and I'll explain how I do it. So we first started with 0.200 moles over liters, right? We multiply that by the liter amount, so it'd be 0.0444 liters, okay? And then now what we do, we have, sorry, I should have specified, this is moles of calcium hydroxide, okay? So now we have moles of calcium hydroxide. Now for every 1 mole of calcium hydroxide, we have 2 moles of HBr that's used, right? You see that from the reaction stoichiometry, right? So that cancels out. And now what we have left over is we have moles of HBr. And then from there, what we can do is we can use the molarity formula and divide the moles by the molarity, right? So it'd be 0.125 moles of HBr over 1 liter. Okay, so I like to write it out like this. Whatever works for you. If you want to figure out the moles first and then use the stoichiometry and then use the molarity formula, you can. I think that the way I do it is probably the fastest way I do it, like the fastest way you can do it. So I'd honestly say it's probably worthwhile to try to learn how to do this. But anyways, let me put it into calculator. So 0.2, right, times 0.0444 times 2, and then times 1 over 0.125. And this will give you the liter amount, right? So we got this value. And so then from there, right, we can take 1 liter and multiply it by 1,000 milliliters, right? And that'll give you the milliliter amount. So times this by 1,000, and we'll get 142. And so that's where 142 comes in. Okay? Does that make sense? Any questions about that?
Yeah, that makes sense.
Okay, sounds good. Yeah, so I like to do it like this, just so I'm not like, I know that there's a way you can use like the dilution formula, but that only works if you have equal amounts of H plus and OH minus, like in terms of the acid and base. But in this case, yeah, I feel like writing the reaction is the best way to do it. But anyways, does anyone have any questions about this or anything? About these questions or anything like that?
Could you go over number 22?
Yeah, sure. So, yeah, this is a good question. So number 22, we're asked to figure out which one will have the highest temperature if at the same thing. Sorry, if at the same initial room temperature. And so the way this works is this is kind of a conceptual question. You could theoretically take all these values and then use Q equals MCAT and try to solve for that, but that's so much work. What would be better to do is understand it, right? All specific heat, what that represents is it represents the amount of energy needed to raise 1 gram of that substance up 1 degree Celsius. All right, that's the definition of specific heat. I'll repeat that. Specific heat capacity represents the amount of energy required to raise 1 gram of that substance up 1 degree Celsius. So what that means is that specific heats that are lower will actually heat up faster because that requires less energy to raise it up one temperature. So when you look at something like gold, right? Gold has a 0.126, right? In comparison to the other ones, it's the lowest one. So what that means is it needs to take 0.126 joules to raise 1 gram of that substance up 1 degree Celsius. So that means it heats up really fast. That's the whole idea. Whereas something like water, right? Water has 4.184. It's a lot of joules. That's why it takes more energy to heat it up. And so that's why gold in this case would be the thing that would have the highest final temperature. Does that make sense? You good with that? Aki? I'm gonna take your silence as yes. Okay. That's also why like water, like oceans, right? They take a while to heat up and cool, and that's because of the specific heat capacity of water. You guys will learn, I guess, more about that later. But all right, any questions about this page? Any other questions that we can go over? Alrighty, then I'm gonna move on. We can do yeah, I'm gonna let you guys work on all the rest of these. So there's what's the word? Like there's um 15 questions or so, right? So I'll give you guys another 15 minutes to do it. I know you guys probably already did it or you may have done it or whatever, but yeah, I'm gonna give you guys 15 more minutes just because of time's sake. Um, and then after that, we can go over any questions that you guys see fit. All right? Sounds good. And yes, please let me know if you guys have any questions. You can text the co-host of this Zoom as well. All right? We will come back around 2:15. Alrighty, we're back. Sue, let me know what questions you want me to check out. I know that some people already messaged me. And so we'll get started on some of those questions. So one question that someone asked me to do was question 23 and 24. With this, basically what we're having here is we have some compounds, reactants and products. We have this reactants balance and everything. And we're asked to find the delta H, right? The enthalpy of this reaction. And so I didn't give you guys a lot of space. Sadly, that's kind of annoying on my end. Sorry about that, but let's get started with this. So what I typically like to do with these kind of questions is I like to, what's the word? I like to kind of split this up because it can be a little confusing if you do it all at once. So I'll do the products first, and then I'll do the reactants, and then subtract the two. So with the products, right, we don't have any oxygen because oxygen is an element. Oxygen is like naturally like found in nature, so there's no delta H formation of that. So all we have to do is do 4 times negative 45.8, right? So that's the products. And then for the reactants, we have water liquid and we have nitrogen monoxide gas. So we have to use this one and this guy. So there's 6 waters, or 6 times negative 285.8, right? Okay, let's move that back down. And then plus 4 times 90.2. All right, just double check if everything's right. Looks like it is, so I'm gonna put this in my calculator. So let's do that. So we see that's 4 times negative 45.8, okay? And we got that value. We got 6 times negative 285.8 plus 4 times 90.2. And we got this value. And we do this minus this because it's products minus reactants. And so I got this value. I got 1,070, positive 1,070. And so we see that that's choice B. Okay. Any questions about that?
Wait, how do you get a positive?
How do we get positive? Because it's products minus reactants. So this value here is negative 183.2, and we subtract it by this value that we get here. So when we do this value in the calculator, we saw that this value is around negative 1354. And so then we do products minus reactants. All right. Does that make sense?
Yeah.
Okay. And then yeah, question 24. This is based off the kinetic molecular theory, right? So the kinetic molecular theory is basically the theory that postulates about like ideal gases, right? And so ideal gases, just as like a good characteristic you should know, they are gases that aren't exerting any attractive forces on each other, right? So when we think of like PV equals nRT, we're not assuming, or we're assuming that there's no attractive forces happening within the gas itself. We're also assuming that it has constant random motion, right? So that means that it's just constantly moving. We also consider that, yeah, like it exerts pressure on the container through collisions with the container. We don't really consider the volume of the gas because that would like, yeah, we always say that the volume of the gas would be the container itself, but the reality is that the gas actually takes up some volume, right? So the correct answer for this, because this for not, would be C. This is basically a concept kind of question. And so if you're having some trouble with this, I definitely say to check out the kinetic molecular theory and just make sure you have those ideas in mind. Okay. Is there other questions? Let's see. Okay, so I'll go over 26. Yeah, so we're asked to find which ones violate the octet rule. Yeah, so we see here that PBr5 does violate the octet rule because PBr5, yeah, it bonds to 5 different elements, right? I don't really think I need to draw that out. NO2, right? We talked about this in class, but this actually has a odd number of electrons, right? If we count out the valence electrons, it'd be +5 plus 12 electrons, which means it's around 17 electrons. And so if we drew this out, like it would be a really weird structure where there's going to be like one missing electron or something like that. And so that's why B would be wrong. Sulfur, or not wrong, it would violate the octet rule. Sulfur tetrafluoride, that's 6 plus 30, sorry, 6 plus 28, which is 34. If I drew all these things out, it would be something like this. And then it'd be 8, 8, 8, 8. And then there'd be 2 extra electrons on sulfur, like that. That's how it would be. And then for boron trichloride, this is a electron deficient molecule. So that means that there'll only be bonds like this. So that's why all of them violate the octet rule. All right. All right. Any other questions or any sort of concerns about these questions that you want me to go over?
Can we go over 36?
36 sounds good. Let's see, 36. So all these questions kind of go hand in hand here. So we're asked to figure out the volume of the container using the information given. And so, yeah, so what we need to do first is we actually need to figure out the moles of each of these guys. And then by finding out the moles of each of these guys, we can figure out the total number of moles. So let's do that. So we got 120 grams, 175 grams, and we got 150 grams. All right. Does anybody know the molar mass of sulfur tetrafluoride? Does anybody have it like in their work or anything? Or hey,
108.052.
108.052. All right. What about for the molar mass of phosphorus trifluoride? Yeah, phosphorus trifluoride. Yeah. Does anyone know that one? Phosphorus trifluoride? Oh wait. These no. Anybody? Does anybody know it? All right. I mean, I'm just gonna let me let's see. I'm gonna go over to the files so I can pull up the answer key just so I don't waste time trying to figure out the molar masses. Oh, that's not, you should not be seeing that. I need to show this. Okay. Where is it? Oh, all right. So here's all the molar masses, or here's the moles. All right. I calculated from previous things like the moles, right? So I'm just gonna write the moles out just so that we can save some time. We do this by calculating them, like using the molar mass and then calculating the moles, right? So for sulfur tetrafluoride, we have sulfur tetrafluoride, we have 1.388 moles, right? For TF3, we have 1.36 mole. And then for ClF3, we have 1.89 mole. So in ideal gases, all of these moles of gases actually can be added together. And so what we can do is we can add all these gases up to get a total number of moles. So if we add these all up, right, we can get 4.64 moles, which is the total mole, right? And we can use that to figure out the first question. Sorry, I'm just gonna put total here. And so from there, if we have a certain number of moles of gas in a container that has a total pressure of this, and this, we have a temperature, we can do PV equals nRT to solve for the volume, right? You might be asking how. We can use the total pressure. So yeah, we can V equals nRT. Because we have the total pressure, we can figure this out. So it'd be 4.64 moles, right? times 0.08206 times 45 plus 273 is 273 plus 45. I'll just use my calculator because I'm not doing that right now. My brain's fried. Where is it? Where's my calculator? There's my calculator. All right, so 45 plus 273.15 is 318.15. Okay. And then pressure is 17. Okay. And then we put it all into calculator. So 4.64 times 0.08206 times 318.15. And we divide it by 17. And we should get our answer. So we see that that's 7.13. And we see that that's A. All right. So the whole idea with this is you can calculate, because of the ideal gas law, you can actually add up all these moles together and use this to figure out the total volume of the container in that way. It only works with ideal gases for sure. But yeah, any questions about that? Okay, if not, yeah. Is there any specific question you want me to go over? Anything at all?
Can we go over
Can we go
32?
over 33?
32 and 33. All right. Well, it works out. So this is we have a reaction forming, right? It's chemical reaction says. We're reacting potassium fluoride and iron 3 nitrate, right? So 32 and 33 kind of go hand in hand. So that's actually a good thing that you guys asked that. So first things first is we have to write out the reaction. So potassium fluoride reacting with iron 3 nitrate, right? Make sure you know your polyatomics. And then that reacts. And so when you do these kind of reactions, I like to call them double replacement. That's actually a term you can call these reactions. What that means is that they're just simply going to like replace one another, like the cation. So if you look at it, right, Fe is going to go with fluoride like that, and then K is going to go with nitrate like this. And so what we can see here is we need to balance it with 3 and 3 like that. Okay, so that's the first step. And so what we see here is they give us a certain reactant amount of potassium fluoride, and they give us a certain amount of potassium nitrate. And so when they ask about the mass of precipitate, we have to actually do some stoichiometry. All right. So let's do that. We have to do some stoichiometry to figure out the mass of the precipitate. And specifically limiting reactant. That's what I meant to say. Because we have two different reactant amounts and we need to figure out the mass of potassium fluoride. I can tell that automatically because I know that nitrates will be soluble. Anything that's bound to nitrate is soluble. And so what we need to do, what I tend to do with these kind of questions is I like to make two lines. I'm going to do one here where I'm taking KF's initial amount. And over here, I'm going to do iron 3 nitrate. So FeNO3 like so, FeNO3 like this. And so I'm going to start off with iron 3 nitrate. So we have 1.3 moles over liters, right? That's the molarity, times 0.0325 liters. And so now we have moles of nitrate. And now for every 1 mole of nitrate, you're producing 1 mole of, oh, hello, why is my thing not working? Oh, it's white. Why is it white? Why did it turn white? Okay, 1 mole of Fe NO3, you're producing 1 mole of FeF3. And because of that, now we need to figure out the molar mass. So I know that iron is 55.85, and I believe fluorine is 19 times 4, right? I believe that's right. So is that the right molar mass? I think it is. I think so. Can anyone confirm or deny? Is that the right molar mass for iron 3 fluoride? Yeah, I'll just check it. Let's see. Check. Iron 3. And I did not. Did I write that right? 112.8. Did I? Why did I write that right? Okay, I don't really, I need to, when in doubt, look at the periodic table. Let's see, where's the periodic table? Periodic table. Oop. Iron 5.19. Yeah. Okay, it should be around that. Oh, did I put times by 4? Why did I do 10 by 4? My bad. Sorry. Times 3 is 112 point. Yes. Okay. Thank you for letting me know. All right. Okay. So yeah, 112.85. See, even I can sometimes get tripped up on the numbers. That's why it's really important to make sure you're doing everything around the calculator. And so this is one like reaction we can like, this is one calculation we can do. So we're gonna do it. Let's do it. So 1.3 times 0.0325 times 1 times 112.85. Okay. So I got around, yeah, I got around 4.77 grams. Okay. But wait, we got to do KF as well, right? Because it's a limit reactant question. So let's do that. So KF, right? We got 0.125, or let's get the 0.565 moles over liters times 0.125 liters times for every 1 mole, or sorry, where for every 3 moles of KF, 1 mole of F3 is produced, right? Okay, and then timesing that, we get 1 mole over 112.85. And then that should also give us an answer. So let's see that. 0.565 times 0.125 times 1 over, or let's do parentheses 1 over 3, close parentheses, times 112.85. And we get a value of 2.66 grams. All right, and that's why choice A is correct, because we see here that with this amount of KF, we're producing less amount of product than we are with the amount of iron 3 nitrate, right? We see that this is more than this, right? And the reason being is that iron 3 nitrate is in excess. So this is excess. Okay, so that's why 2.66 works. Does that make sense for you guys? Okay, I'm gonna take a silence as yes, it does make sense. Okay, and then with that, using the ions given, right, we can see here that, yeah, like what would be remaining? So obviously KF would be remain, or sorry, obviously K and nitrate, potassium and nitrate would be remaining, because that's the aqueous product of it. So anything with K and F, or K and nitrate should be there. So B wouldn't make sense. A wouldn't make sense, right? Um, and D also wouldn't make sense. And so we are left with C and E, right? And so we know that iron 3 nitrate is in excess. And so what we can assume is that not all of the iron 3 ion is actually going into the precipitate. So because it's in excess, not all of this is going into this. There's some iron 3 that's not being reacted fully because KF is limiting. And so because of that, there actually is going to be some iron 3 left over in there. There's not going to be any KF because all the fluoride ions were reacted with to form the iron 3 nitrate, or iron 3 fluoride. Okay, does that make sense for you guys? Yeah, you guys good with that?
Yeah.
Okay, any other questions?
Wait, I'm sorry. Can you explain that one more time?
Yeah, sure, no problem. So, what's happening here, right? We're mixing these two things in a beaker, right? We got iron nitrate, okay, and we got KF. And what's happening is we are creating, iron 3 fluoride, and then obviously K nitrate is aqueous. Okay, we know that Kf is limiting, meaning that this is going to run out. This reactant is running out. And so what that means is running out is that all of Kf is going to be used to react to form this precipitate. So all of the fluoride ions will react and go into this precipitate, like all of them. But then for iron nitrate, because we figured out that this is excess or there's more of it, or not that there's more of it, but that it's not going to run out, obviously some of the iron is going to go into it, but because there's more iron than needed to facilitate the reaction, there's going to be excess iron plus ions in this. Okay, so obviously you have the precipitate, you have iron plus ions, and then you're also going to have the stuff in the aqueous. Okay, so not all. Or iron plus 3, sorry, I should have said iron plus 3. But yeah, not all of the iron plus 3 is going to be made into the iron 3 fluoride. And so there's going to be some iron 3 fluoride within that resulting beaker. Does that make more sense? Okay. All right. So do you guys have any questions about anything else? Please let me know. Anything else?
Yeah, I have one. Question number, sorry, 30.
Question 30?
Yeah.
30. All right. Quantum numbers. So Rowing, blah, blah. I don't really need to know whatever that element's name is, right? I know it's 6p, right? So 6p has to have n equals 6, right? That's what 6 represents. And a p orbital has to be L equals 1, all right? That's something that we should be familiar with, right? Right? L equals 0 will be S, right? L equals 1 is P, L equals 2 is D, and then L equals 3 is F, right? So L has to be 1. And but just by knowing that, we can figure out everything else, right? There's only one answer choice here that has L equaling 1, and that's choice C. So that's how you would represent all the electrons in that quanta, in that orbital.
Okay.
All right? Yeah. Any other questions? Okay,
Um, I have a
yeah.
question that's kind of like general.
Mm-hmm.
So for like the final with Mina's test, Professor Yusuf's, I mean, would it be like kind of like this length and this many questions?
Yes, it'll probably be something similar to this, probably this length. If anything, what he's doing is he's going to take this document and then definitely reword the questions, but have the same sort of kind of questions where they're asking similar topics and ideas. Yeah. So it'll be around this length because you guys are going to have 2 hours to do it. And so 40 questions or so is somewhat reasonable for 2 hours.
Okay.
Mhm. Any other questions? Anything in specific or whatever? Okay. If not, um, yeah, I guess I will let you guys go then. Um, yeah. Feel free to email me if you guys have any questions. I'm always here for you guys. Um, yeah, you guys have a lot of resources for sure. So let me know if you guys need any help with anything. I have a final tomorrow, so I'll be up a little late. So if you guys have any emails or anything, feel free to let me know. Um, and yeah, you guys can do this. All right. I know we've had like a pretty challenging semester or so. I know it's your first semester, but be proud of yourselves. You guys got through it. I'm proud of you guys, and you guys can do this. Okay. Let me know if you guys have questions or anything. And yeah, I guess I'll end it here. Um, yeah, I hope you guys have a wonderful day and take care. Bye, guys. Hey, Yusuf,
Well,
listen,
I have one quick question.
with the B value, is that what you're
Yeah,
asking?
yeah.
Don't really worry about that. He's not going to ask that much of the point of that formula is so that you can see that there's like you have to actually take into account volume of the gas and also the attractive forces of the gas.
Hmm. But
Okay?
in general, the correction is the same rule. They just the heavier, the more the correction.
Yeah, the heavier it is, the more correction. Yeah.
Okay, cool.
Does that work
Thank
for
you.
Okay.
A as well?
I don't know what A is. What is A?
Pressure.
Yeah, so same thing with pressure. Yeah, the more heavier it is, the more correction because the heavier it is, um, yeah, like it'll affect the collisions and stuff. So yeah, it's the same thing.
Okay.
All
Okay,
right. Good luck in Nirvana.
of course, no problem.
Thank
Yeah,
you.
no
What
Bye.
final?
problem. Have a good day, guys. Love you
What
guys.
Bye.
final
Bye.
do you have tomorrow?
Research literature.
Isn't that like presenting with Letsu?
Uh, give me a second. I have to stop the recording.